4 different groups attached to it, you can get the S or the R, you go. No big deal. Okay? Because when you get the carbocation, you attack from the top or the bottom. Okay? So you don't have much control. 50-50 racemic mixture. If I put this in a polarimeter, is it going to deflect the angle at all in a polarimeter if I put a mixture of this? No, it's 50-50, so it'll be 0. Okay. So if I give you a question where, oh, you did this reaction, you put the contents in a polarimeter, and the degree is 0. You're immediately going to think either the molecule is achiral or it's a racemic mixture. Has to be one of the two. Okay. You can't tell. Okay. Unless you're given information beforehand. It's going to be racemic, right? Okay. So this is just explaining what I just talked about. Here it is when you get the secondary carbocation is flat. A carbocation is still sp2, right? There's an empty p orbital there, and therefore the reagent that's going to attack it from the top or the bottom. Let me remind you, when you have the alkene and it has a acid, the alkene is a nucleophile, it attacks the acid, correct? Nucleophile to electrophile, it attacks. That's step 1. Now you get a new molecule. That new molecule is a carbocation. That double bond, when it attacked, now the molecule has a carbocation. Now that molecule is an electrophile or nucleophile? It's an electrophile now. You convert it. It's a nucleophile first, did a little reaction here. Now that molecule is completely different, and it's now the electrophile. Now another nucleophile will come in and attack that electrophile. One step after another. Don't think that the starting material is a nucleophile. Okay, I know that alkene is a nucleophile, so therefore it stays a nucleophile the entire time. That's not it. It's just like that for the one reaction. New molecule, new assessment. Where are the electrophile, nucleophile? Does a reaction. New molecule, the electrophile, nucleophile. Next reaction, and so forth, right? We're just playing this game with nucleophile, electrophile, and we can switch it. Empty p orbital, the water can attack from the top or the bottom. That changes, and the stereochemistry makes it racemic. You get RS, and so forth. Reminder, if you have a molecule that is chiral, you have a molecule, imagine, molecule, it's chiral. That means you put it in a polarimeter, it's not 0, it's going to be plus or minus. You don't know which plus or minus, you have no idea, but it's going to be a plus or a minus. It is a chiral molecule, pure chiral molecule. It has multiple stereocenters within it. Just say it has 2 stereocenters in it. So that's the actual sp3 locations within the overall molecule, right? Just getting the language correct. Each of those stereocenters within it, say there's 2. It's an R and an R in there when you do the RS stuff. It's an R and R. You take that molecule, it's chiral, there's no mirror plane in it. You put it in a polarimeter, deflects that angle somewhat. It's chiral and has stereocenters. For its enantiomer, that molecule, is it RR? What is it down? SS. Every stereocenter has to change. Everyone, not one, all of them have to change. So it has to be, it was RR I said, so now it has to be SS. Okay? Now that molecule is also chiral. And when you put it in a polarimeter, it will be the exact opposite of the first molecule, that was RR. If RR was plus 30, the SS is minus 30. If you put a 50-50 in there, it's going to be a 0. Okay. RR has to be SS, then there are pairs called enantiomers. If it's RR and it goes to RS, we only switch one of the stereocenters. What is the relationship between these 2 molecules? Diastereomers now. They are diastereomers. Okay? Because not all the stereocenters switched. Only some of them switched. You can have R, like 50 of them, some gigantic molecule. You can have the other molecule, which is S for 49 of them, but one of them is still an R, diastereomers. Okay? They have different properties, different behavior. Okay? You have to have this nailed down. This quick review, right? To move on. and side. Okay, re and side just means that it's not R or S yet, it's a double bond. But it has the potential, we know that attacks there is going to become an R. When it attacks there, it can become an S. That's what we call pro-chiral, pro-stereocenter. It's a stereocenter, it's not chiral yet. It's cool hanging out as an alkene. But I see the potential. It can become an R, it can become an S. That's what this means. Re and side businesses, re and side phase. So I'm not going to test you on that, but it's just to be complete. Okay. This is the same stuff we just talked about. Okay. Let's do this last one here. So here is a chiral alkene. Okay. Now be careful. When it says chiral alkene, that doesn't mean the alkene is chiral. That means the molecule is chiral. The molecule is chiral, but just happens to have an alkene in it. So be careful with their language they're using. The chiral part is always the sp3. Okay. See this carbon here? Is this carbon sp3? No. Is this carbon sp3? No. They're sp2. They're flat, 120-degree angle. They cannot be RS. They cannot be chiral. Stereocenters. Okay. Let's go around the ring. Here's a carbon that's, is this sp2 or sp3 right here? That's sp3. Okay, that's cool. It's the first requirement. Does that have 4 different things attached to it? No. There's 2 hydrogens here, so that's it. We're done with that one. We go down the chain. How about this carbon here? Does it have 4 different things attached to it? It's sp3, great. 1, 2, 3. 4 different things. So that has to be a stereocenter. Then we can do the RS over here. Okay? You want to tell me if this is RS? What do you guys think? What do you guys think about this one here? Where's number 1? What's position 1? We got this ethyl group, we have a methyl group, and we have this CH2C double bond C. Which one is 1? 1, 2, 3, 4. We know the hydrogen is 4. So which one is 1? The what? This alkene group side here? Yeah. That's the bigger group, right? This carbon has 3 things attached to it. This carbon has 2 hydrogens. This carbon has 3. This carbon has 2 hydrogens, but now it has yeah, double bond. Go down the chain. So this has to be number 1. This is 1. This is 2. This is 3. This is 4, correct? So we go 1, 2, 3. That looks like an R to me. Right? And the hydrogen is already in the back, so it's beautiful. It's just the R. Clockwise, R, and the hydrogen is back. If the hydrogen is towards you, no big deal. You count the exact same thing. It's an R, oh, it's taken the wrong way, so I switch it to an S. Right, the rules. You guys know this. Okay. So here we have it. When we add the acid to it, this will pick up the proton. We know we're going to get it on the secondary carbon. Now, remember, you have an alkene. It's a nucleophile. It goes and attacks, in this case, protons. Picks up a proton. You're left with a carbocation behind. The carbocation is what, in this case, secondary. It's pretty stable. It's going to do the secondary versus the primary, right? That's the choice it has. It's going to go to secondary. But you all know that, oh, secondary is pretty good. But before you do the rest of the question, like secondary is pretty good. Can it become a tertiary? Can it become delocalized? Can that secondary carbocation somehow get extra stability? Is there a hydride shift where it can become tertiary? Is there other double bonds or lone pairs that can help donate in and move around this plus charge or whatever? In this particular case, that's not the case, right? You get a plus charge over here. The one beside is a CH2. What can that do? It can shift over a hydrogen, well, we're still a secondary. So it's not going to do that. It has to go up the chain. It has to be a tertiary carbocation or delocalization. That makes sense, everybody? Even though there's a one over here that could become tertiary, it doesn't become a secondary carbocation, secondary carbocation, secondary. It keeps walking out until finally it finds a tertiary. It has to be right beside it. It has to be alpha, the next bond to it. Does that make sense, everybody? Okay. It doesn't sense that turn all the way over there, it just can't move down the chain, it's just very close to it. This case is that it cannot gain extra stability. It's a simple case, it stays there, and now it's a MPP orbital, the water can attack on the top or the bottom. Okay? And that's where you get these two loops here. These two molecules. Everybody okay with that? It's not that big of a deal. Let's go stepwise. Okay? Keep track of the wedges and the dashes of what happens. All right, that's it for that chapter. Let's get on to alkynes. So alkynes are fun. They're not that bad because they're similar to alkenes. You know already the reaction to alkenes. It's just an alkyne. You do a reaction, well, you still get an alkene. Then you can enter the alkene system.